Hello students. Today we're going to be looking at the engine of discrete mathematical proofs, which is mathematical induction. So often students are taught induction is like a row of falling dominoes, like described in the previous video. While that's a fine visual, it glosses over the actual uh, foundational axiom that makes it work, and that is the well-ordering principle. And basically, the way this works is if you take any non empty collection of natural numbers, no matter how chaotic it is, we can always find a smallest element. So to put this in more formal terms, we're going to say for every, and this symbol is basically denoting for every or for all non-empty subsets of n, and well, this symbol is just saying there exists a least element. So I'm just going to briefly or non-formally introduce you to some of these symbols we use in proofs. And yeah, so today we'll see how this bedrock truth guarantees that induction isn't just hand waving, it's an ironclad logical guarantee. So let's now formalize the principle, or let's look back into the example of the dominoes, right? So in the previous video, we built the natural numbers themselves, and we started with the Peano axioms and discovered something remarkable, which is one of the axioms, the induction axiom, guarantees that our number system doesn't have any pieces. So let's first consider this primary example, which is 1 plus 2, and just going off infinitely to n. So the sum of all natural numbers is equal to this right-hand expression. And it looks unbelievable, right? For anyone who's first seen this, we can check it at n equals 1, check it at n equals 2, check it at n equals 3. But mathematics doesn't care how many examples you checked, right? You can check 1,000, it's not a proof. 1,000,000, it's not a proof. A proof must explain why the statement is true for every single natural number, and that creates a problem, right? There are infinitely many natural numbers. So how can a finite human being write a finite proof that establishes infinitely many cases? And that is where mathematical induction steps in. So yeah, right. Back to the first example, right? The domino machine. We're going to once again draw a long row of dominoes going off infinitely. 1, 2, 3, 4, 5. So the first step, right, as mentioned in the previous video, the first domino falls, and then after that, any domino knocks over the next. And the best intuition for induction is still the domino analogy, right? And after imagining the infinitely long line of dominoes, right, the goal is to prove every domino eventually falls. And at first, that sounds impossible, right? There are infinitely number of dominoes, and surely we would need infinitely many checks. But here's the thing, right? We only need these two facts right over here. If these two facts are true, then the entire chain collapses, right? So domino 1 falls, so domino 2 falls, so domino 3 falls, etc. And the process continues on forever. So the beauty is we never directly checked, domino number 5,000. The chain reaction is what did the work for us. And this is exactly how mathematical induction works. So the formal structure is given a statement, a mathematical statement, P of n. So I guess in order to prove this mathematical statement, P of n, for all n that is an element of the set of natural numbers, we need first what is called the base case, which is, going back to the domino analogy, establishing the anchor point. And then the second is the induction step. So the base case, as mentioned earlier, is going to be P of 1. And then the induction hypothesis, what this is saying is, given or assuming P of n, that statement holds true for P of n plus 1. So Ross induces induction directly from this, and yeah, our objective is to use these two statements to make our induction proof. So we're going to be looking at a couple of examples again. Now let's go back to that original example, right, of 1 plus 2 n is equal to n times n plus 1 over 2. So let's establish the base case, right, for P of 1. So left-hand side, right, for the first, we're only considering the number 1 is equal to 1 times 1 plus 1 divided by 2. This happens to be 2. So this cancels out, so that is equal to 1. So now we have verified that our base case is correct, and it works. Now, this is where the inductive step comes in. We replace the first portion using the induction hypothesis. Well, okay, so first 1 plus 2 plus, just going on to n. Now we add n plus 1 to both sides. And then we can just simplify this, right? So let's just say, yeah, we factor out the n plus 1 so that it's n over 2 plus 1. We can further simplify this down to n plus 1 times n plus 2 over 2. So notice this, right? That's exactly the formula with n plus 1 substituted for n, right? If we look back to this original statement, if we're considering P of n plus 1, what is that equal to, right? That is precisely equal to n plus 1, considering this, right? Times n plus 1 over 2, which is precisely this. So that's exactly how we do induction. We've shown that this statement holds for every natural number now. So this is where many students get confused. When we do the induction step, we are not proving P of n plus 1 outright. We are proving the implication of P of n directly. The same P of n also holds true for P of n plus 1. So Ross, the textbook elementary analysis, emphasizes this point. We prove that if one domino falls, then the next one falls. That alone doesn't start the chain. The base case is what starts the chain. So the induction step is what keeps it moving. If either price is missing, either piece is missing, the proof fails. So this is why every valid induction proof always contains both parts. We can't just start with the induction step. So now let's look at a, I guess, more difficult example. and it's going to be this. And our claim is that for all n, this statement, this expression is divisible by 16. So basically how we can write this is we say that that's kind of how we can write it, as this left side is a number that is divisible by 16, right? So the key trick to this, right, is, okay, first let's do the base step, actually. Let's not get ahead of ourselves. We check the first case, which is n equals 1, or sorry, p of 1. So 5 to the 1 minus 4 times 1 minus 1 is equal to 0. So, and obviously 0 is divisible by 16, so that checks out. So now we assume, right, I guess the induction step, which is going to be five to the n plus 1 minus 4 times n plus 1 minus 1. And I guess the thing is you have to like really think of how to, I guess, like reverse engineer it. So I guess the clever thing is we factor out a 5, right? 5 to the n minus 4n minus 1. But this isn't exactly true, right? Because we have this part, so we actually have to do plus 16n at the end. So that way, when we distribute this, it's really saying 5, just it's 5 to the plus 1 minus 20n minus plus 16n minus 5, right? So what we've done is just cleverly distributed and then added this remaining term here at the end. So this is 4n, so this statement still holds true. So now that we've done that, let's see here. And also, yeah, right, so the 4n plus 1 can be rewritten as 4n plus 4 4n, it's technically negative, 4n minus 4 minus 1, which is why it's negative 5 works out. So this is what our what we can rewrite this as. So look carefully, right? The first term is divisible by 16 because of the induction hypothesis. The second term is also obviously divisible by 16, right? So we look at this, right? We've proven the base step. So we know this here is divisible by 16. And because of that, this implies that even with this coefficient, this number is still going to be divisible by 16. And if we look at this part, right? This is obviously divisible by 16 simply because we have this 16 over here. So the induction step, therefore, works. So this teaches us an important lesson, which is induction is often less about brute force algebra and more about finding the right algebraic rewrite. So now let's look at a, I guess, even more difficult example. We're going to be looking at the sum of squares. This is Ross exercise 1.1. So let's do the base case, right? First. So p of 1, doing n equals 1, and let's see here, right? 1 times 2 times 3 divided by 6 is equal to 1. So we've just shown our base case works. So now we look at the induction step, which is we add n plus 1 squared to both sides. So let's see here, n times m plus 1 times 2m plus 1 divided by 6 plus m plus 1 squared. So now let's do some simplification. Let's first substitute out an n plus 1. So we are left with n times 2n plus 1 divided by 6 plus m plus 1. So yeah, this example shows the standard rhythm of many induction proofs. We just first get the assumption, then substitute, then simplify here, right? So notice how this first step here, we just continue the simplification, and after some algebra, we are left with n plus 1 times n plus 2 times 2n plus 3 divided by 6. I encourage you to do the work yourself to verify this statement for practice. And right, this is the exact same statement if we were to plug m plus 1 here, right? Let's just verify that, right? M plus 1, this would just become plus 1 times our m plus 1 times 2 times m plus 1 plus 1 divided by 6, which does in fact become this. Now let's look at a harder problem, which is going to now involve some trigonometry. And we're going to say that this holds for all x that is an element of the set of real numbers. So for every positive integer n, every real number x, the absolute value of sine of nx is less than or equal to n times the absolute value of sine x. And this is substantially harder because trigonometry enters the picture. And let's start out with the base step as usual, which is going to be P1. So sine of x equal to 1 times sine of x, right? So we've just shown that this works. Now let's look at the induction. So using the addition formula, we can write sine of m plus 1 x is equal to sine of nx plus x, and which is equal to sine of, this is a little more complicated because you do have to use trig identity. And we take the absolute values. And to solve this, we have to use something called the triangle inequality, which is basically, let's just first write this, sine of plus 1x is less than or equal to sine of nx times cosine x plus cosine nx times sine x. So basically what the triangle inequality is saying, at least, is if you're given in a, I guess, expression or equation with like 3 terms, you know for certainty that the one side, one term, is always going to be less than or equal to the other 2 terms, right? So if you notice, after taking the absolute values, right, this term is less than or equal to these 2 terms here. And I can make another video on proving the triangle inequality, but this is a very useful, I guess, tool in induction and also later proofs. So do get accustomed to this. So now let's look at that, right? We've applied the triangle inequality, and now we have to use, really have to think about the essence of trigonometry, right? There's two key facts, right? Cosine of x is always going to be less than or equal to 1. So therefore, cosine of the absolute value of cosine of nx is always going to be less than 1 as well. So what we can do now is say sine of m plus 1 x is less than or equal to 1 times the sine of nx plus 1 times sine of x, right? And this is true because of these facts. So sometimes you're going to have to make these important, I guess, use this important knowledge to your advantage to continue reducing your statement. So now we apply the induction hypothesis, right? Which is, so yeah, we've obtained this statement. And now what we can write is this statement over here is less than or equal to m times sine of x plus the absolute value of sine of x is equal to m plus 1 sine of x, right? So now just notice that we have fulfilled this, right? This is the right side equation, and we've just shown that this holds for m plus 1. So that was a little more difficult question. I would definitely look at problems with trig, because those are some of the more difficult levels of, I guess, the induction proof. And this is important because it demonstrates that induction isn't restricted to sums and divisibility. It appears throughout analysis, algebra, trigonometry, combinatorics even, and computer science. So today we've learned one of the foundational proof techniques in mathematics. We begun with the seemingly impossible task, and we found how can a finite proof establish infinitely many truths. So the next video is going to be discussing the rational numbers and proving, I guess, we're going to be constructing the rational numbers and seeing how mathematics expands beyond the simple counting. So thank you for watching, and I'll see you in the next video.